Introduction: the discovery that changed everything. In 1998, two independent teams of astronomers announced a discovery so shocking, so completely unexpected, that it fundamentally transformed our understanding of the universe and its ultimate fate. What they found was so contrary to everything physicists expected that many initially refused to believe it. These teams were studying distant supernovae exploding stars that briefly shine as bright as entire galaxies. They were using these cosmic explosions as standard candles to measure how fast the universe was expanding at different times in its history. Everyone expected to find that the universe's expansion was slowing down, gradually decelerating due to the gravitational pull of all the matter it contains. Instead, they discovered the expansion was speeding up. The universe wasn't just expanding, it was accelerating, expanding faster and faster as time goes on. This discovery earned Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics. But more importantly, it revealed that something deeply mysterious dominates the universe. An unknown form of energy that pushes space itself apart, overcoming gravity's pull, causing the cosmos to expand at an ever-increasing rate. Scientists call this mysterious force dark energy, though that name is really just an admission of ignorance. Dark energy is one of the most profound mysteries in all of science. We know it exists. Its effects are measurable and undeniable. We know it constitutes about 68% of all the energy in the universe, making it by far the dominant component of reality. Yet we have no idea what it actually is. Dark energy determines nothing less than the ultimate fate of the universe itself. Will the cosmos expand forever, growing darker and colder until the last stars burn out and entropy claims everything? Will the acceleration eventually tear apart galaxies, stars, planets, and even atoms themselves in a catastrophic Big Rip? Or might dark energy change over time in ways we can't predict, leading to outcomes we haven't imagined? These aren't just academic questions. They're about the deepest possible issue: what will become of everything that exists? Understanding dark energy means understanding how the story of the universe ends. This journey will take us from the discovery of cosmic expansion through the shocking realization that expansion is accelerating into the strange physics of empty space, and finally to the various scenarios for how everything might ultimately end. Along the way, we'll encounter some of the most mind-bending concepts in physics: vacuum energy, quantum fluctuations, the cosmological constant problem, and the heat death of the universe. Fair warning, this story doesn't have a happy ending. The universe's fate, as far as we can tell, is bleak. But there's profound beauty in understanding the truth, even when that truth is uncomfortable. And who knows, future discoveries might reveal possibilities we haven't yet imagined. So let's begin with the man who first realized the universe itself is expanding, setting the stage for everything that followed. Hubble's discovery: the expanding universe. In the 1920s, the nature of spiral nebulae, fuzzy, spiral-shaped objects seen through telescopes, was hotly debated. Were they clouds of gas within our Milky Way galaxy, or were they separate galaxies far beyond our own? Edwin Hubble, working at Mount Wilson Observatory in California, with the most powerful telescope in the world at that time, settled the debate. In 1924, he identified Cepheid variable stars in the Andromeda Nebula. These stars pulse with regular periods related to their intrinsic brightness, allowing astronomers to calculate their distance. Hubble's measurements proved Andromeda was vastly farther away than any star in our galaxy. It was a separate galaxy, nearly 1 million light-years distant. This dramatically expanded the known size of the universe. But Hubble's most important discovery was yet to come. By 1929, Hubble had measured distances to numerous galaxies and obtained their spectra, the pattern of light they emit at different wavelengths. He noticed something remarkable. The spectral lines of distant galaxies were shifted toward the red end of the spectrum, indicating they were moving away from us. Moreover, the more distant a galaxy was, the faster it appeared to be receding. This relationship became known as Hubble's law. A galaxy's recession velocity is proportional to its distance. Double the distance, double the recession speed. This simple relationship had a profound implication. The universe itself was expanding. To understand this, imagine dots on the surface of a balloon. As you inflate the balloon, every dot moves away from every other dot. An observer on any dot sees all other dots receding, with more distant dots receding faster. No dot is at the center. The expansion is uniform everywhere. Similarly, space itself is expanding, carrying galaxies apart. It's not that galaxies are moving through space away from us. Rather, space between galaxies is growing, and we're not special observers in any galaxy would see the same pattern of recession. This was revolutionary. Before Hubble, the prevailing view was that the universe was static and eternal, neither expanding nor contracting. Einstein himself, when formulating general relativity in 1915, found that his equations predicted an expanding or contracting universe. He considered this so problematic that he added a cosmological constant term to his equations, specifically to make the universe static. When Hubble's discovery proved the universe was indeed expanding, Einstein reportedly called the cosmological constant his biggest blunder. He removed it from his equations, assuming a simpler universe that expanded due to the initial impetus of the Big Bang while gradually slowing due to gravity. For decades, this was the accepted picture. The universe began in a hot, dense state about 14 billion years ago, the Big Bang, and has been expanding ever since, with gravity gradually slowing the expansion. The key question seemed to be whether the expansion would slow enough to eventually reverse, causing the universe to recollapse in a big crunch, or whether it would expand forever, gradually slowing but never stopping. Everything changed in 1998 when astronomers discovered the expansion isn't slowing at all. It's accelerating. Einstein's biggest blunder turned out to be prescient. The cosmological constant, or something very like it, appears to be real after all. The supernova surveys, acceleration revealed. Type Moye supernovae are remarkable astronomical objects. They occur when a white dwarf star, the dense remnant of a sun-like star, accumulates matter from a companion star until it reaches a critical mass of about 1.4 times the sun's mass. At this threshold, nuclear reactions ignite catastrophically, completely destroying the white dwarf in a thermonuclear explosion. Because type Ia supernovae always occur at the same mass threshold, they have similar intrinsic brightness. This makes them excellent standard candles objects whose distance can be determined by comparing their apparent brightness to their known intrinsic brightness. The fainter a supernova appears, the farther away it is. By the 1990s, technology had advanced enough to detect supernovae in very distant galaxies, billions of light years away. Two independent research teams set out to use these distant supernovae to measure how the universe's expansion rate had changed over cosmic history. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt at Australian National University, spent years developing techniques to find and measure distant supernovae. The work was painstaking. Supernovae are unpredictable, lasting only weeks, requiring careful monitoring of thousands of galaxies to catch them at the right time. Both teams expected to measure deceleration. The question wasn't whether gravity was slowing the expansion, but how much. Would the universe expand forever or eventually collapse? The data told a different story. Distant supernovae appeared fainter than expected, meaning they were farther away than predicted by a decelerating universe. The only way to explain this was if the expansion rate in the past was slower than it is today, if the expansion has been accelerating. At first, both teams were skeptical of their own results. They checked for systematic errors, calibration problems, dust that might be dimming the supernova, or evolution in supernova properties over cosmic time. Every check confirmed the acceleration was real. In 1998, both teams published their findings. The universe's expansion was speeding up, driven by some mysterious force acting against gravity, a repulsive effect that dominated the universe's energy budget. The scientific community was stunned. This wasn't a prediction from theory. It was a complete surprise revealed by observations, and it demanded an explanation. What could cause the universe to accelerate? There were two main possibilities, both deeply mysterious. First, Einstein's cosmological constant might be real empty space. Itself might have inherent energy that creates a repulsive gravitational effect. Second, some unknown field pervading space might be driving the acceleration, similar to the inflaton field thought to have driven rapid expansion in the universe's first fraction of a second. Scientists coined the term dark energy to describe whatever was causing acceleration, emphasizing our ignorance about its nature. Dark energy is literally the energy of the dark, the empty space between galaxies. But calling it dark mainly admits we don't know what it is. Over the following years, additional supernova observations, plus measurements of the cosmic microwave background and the large-scale structure of the universe, confirmed the acceleration and allowed increasingly precise measurements of dark energy's properties. We now know dark energy constitutes about 68% of the universe's total energy. Dark matter, the mysterious substance that provides extra gravity to hold galaxies together, makes up about 27%. Ordinary matter, everything made of atoms, including stars, planets, gas, dust, and living things, constitutes only about 5%. We live in a universe dominated by things we don't understand. Dark energy is the biggest mystery of all, and solving it requires understanding some of the strangest aspects of modern physics. The cosmological constant, energy from nothing. The simplest explanation for dark energy is that it's Einstein's cosmological constant A, property of space itself. But what does that mean? In general relativity, Einstein's theory of gravity, mass, and energy curves space-time. Objects move along curved paths we perceive as gravitational attraction. Normally, we think of empty space as just that, empty, containing nothing, having no properties except geometry. But quantum field theory, our best description of particle physics, suggests empty space isn't truly empty. It's filled with quantum fields, and these fields never have exactly zero energy even in their lowest energy state. Quantum fluctuations cause particles to constantly pop in and out of existence in pairs, borrowing energy from the vacuum briefly before annihilating and returning it. This vacuum energy, or zero-point energy, should contribute to the cosmological constant. Space itself should have inherent energy that doesn't dilute as the universe expands, unlike matter, whose density decreases as volume grows. Vacuum energy maintains constant density because it's a property of space itself. This vacuum energy would have a strange property: negative pressure. To understand why, consider that energy density has units of energy per volume. Pressure also has units of energy per volume. For the vacuum to maintain constant energy density as space expands, the energy content must increase. The vacuum must do negative work as it expands, which corresponds to negative pressure. In general relativity, both energy density and pressure contribute to gravity. Positive energy density causes attraction, but negative pressure causes repulsion. For the vacuum, the repulsive effect of negative pressure outweighs the attractive effect of energy density by a factor of 3. The net result? Vacuum energy creates repulsive gravity, causing accelerated expansion. This sounds like exactly what we need to explain dark energy. Problem solved, right? Not quite. There's a catastrophic problem, perhaps the worst theoretical prediction in the history of physics. When you calculate how much vacuum energy quantum field theory predicts, using standard techniques and reasonable assumptions, you get an answer that's wrong by a factor of about 10 to the 120. That's 1 followed by 120 zeros. The theoretical prediction is larger than the observed value by 100 trillion 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 trillion. This isn't just being a little off. This is the most spectacularly incorrect prediction ever made. If the vacuum energy were as large as quantum field theory naively predicts, the universe would have accelerated so violently that atoms could never have formed, stars and galaxies would never have condensed, and life would be impossible. Yet observations clearly show dark energy exists with a very specific, very small value, about 6x10 joules per cubic meter. This is incredibly tiny on human scales, less energy than a flashlight battery in a volume the size of Earth, but large enough to dominate the universe over cosmic scales and time scales. Why is the vacuum energy so small? We don't know. Physicists have spent decades trying to understand this cosmological constant problem with little progress. It's one of the deepest mysteries in theoretical physics. Some researchers invoke the anthropic principle. In a multiverse with different vacuum energy in different regions, we necessarily find ourselves in a region where it's small enough for structure to form, because that's the only type of region where observers can exist. This explains the observation, but feels unsatisfying. It gives up on finding a deeper physical reason. Others hope for new physics at high energies that somehow cancels most of the vacuum energy contribution, leaving only the tiny observed value. But no compelling mechanism has been found, and such fine-tuned cancellation seems suspiciously artificial. The cosmological constant remains the simplest explanation for dark energy observationally, but it's deeply problematic theoretically. This has led some scientists to explore whether dark energy might be something else, not the fixed energy of the vacuum, but a dynamical field that changes over time. Quintessence, a dynamic alternative. If dark energy isn't the cosmological constant, what else could it be? The main alternative is called quintessence, a hypothetical field that pervades space, similar to the inflaton field thought to have driven cosmic inflation in the early universe. Unlike the cosmological constant, which is truly constant everywhere and for all time, a quintessence field would vary in strength. Its energy density could change as the universe evolves, potentially increasing or decreasing over time. The name quintessence comes from ancient philosophy. Greek philosophers believed everything was made of 4 elements: earth, air, fire, and water. They proposed a 5th element, quintessence, that filled the heavens. Modern quintessence would be a 5th component of the universe after ordinary matter, dark matter, radiation, and curvature. How would quintessence work? Imagine a field with a value at every point in space, like temperature or pressure. This field has potential energy that depends on its value. Think of a ball rolling on a hilly landscape, with the height at each position representing potential energy. If the field is slowly rolling down a very flat potential, it can dominate the universe's energy while creating accelerated expansion similar to the cosmological constant, but with the possibility of changing over time. Different models of quintessence make different predictions about how dark energy evolves. In some models, dark energy density slowly decreases, making acceleration a temporary phase that might eventually end. In others, it increases, possibly leading to catastrophic outcomes we'll discuss later. The key difference from a cosmological constant is that quintessence is dynamical. It can change. This might help explain why we live at a time when dark energy and matter have similar densities within an order of magnitude, rather than dark energy being completely negligible or completely dominant. In a cosmological constant universe, there's a coincidence problem. Why is the current epoch special? Dark energy was negligible for most of cosmic history, but recently became dominant. This seems like an odd coincidence. Quintessence models can potentially avoid this by having dark energy that was always comparable to matter density due to dynamical tracking mechanisms. However, quintessence doesn't solve the cosmological constant problem. You still need to explain why the vacuum energy is so small. Quintessence is an additional component on top of whatever vacuum energy exists. Can we distinguish between the cosmological constant and quintessence? Yes, in principle. The key is measuring something called the equation of state parameter, usually denoted W, which relates dark energy's pressure to its density. For a cosmological constant, W equals exactly 1 at all times. For quintessence, W might differ from 1 and might change over time. Current observations constrain WW to be very close to 1, within a few percent, but aren't precise enough to rule out quintessence. Future surveys measuring billions of galaxies might detect variations in W over cosmic time if quintessence is correct, or they might confirm W equals 1 exactly, supporting the cosmological constant. Either way, the measurements will tell us about dark energy's nature and evolution. There are even more exotic possibilities. Dark energy might be caused by modifications to general relativity at very large scales, or it might arise from extra dimensions of space that manifest at cosmic scales. Or it might be something completely different that no one has thought of yet. The truth is, we simply don't know what dark energy is, but we can predict what it means for the universe's future, and those predictions are stark. The heat death. Expansion forever. If dark energy behaves like a cosmological constant or quintessence with WW near 1, the universe's fate is sealed. Eternal expansion, growing ever colder and emptier until all structure dissolves and entropy claims everything. This scenario is called the heat death of the universe. Here's how it plays out over unimaginable timescales. Currently, the universe is about 13.8 billion years old. Stars are forming, galaxies are evolving, life exists on at least one planet. Dark energy dominates the universe's total energy, but its effects are only just becoming apparent. Gravity still holds structures together on scales from planets to galaxy clusters, but as the universe expands, dark energy's dominance grows. Ordinary and dark matter become more dilute. Their density decreases as volume increases. Dark energy's density remains constant, so its relative importance grows. Within about 100 billion years, galaxies beyond our local group will become unreachable, having been carried beyond our cosmic horizon by accelerating expansion. Any civilization existing then would see fewer galaxies in their night sky than we do. Distant galaxies will have redshifted beyond visibility. By about 150 billion years, the cosmic microwave background, The afterglow of the Big Bang, currently at 2.7 degrees above absolute zero, will have redshifted to undetectable levels. Future astronomers won't have this evidence for the Big Bang that we possess. Star formation will continue for trillions of years, but gradually slow as gas is consumed or expelled. The last stars will form perhaps 100 trillion years from now. After that, no new stars will ignite. The existing stars will burn out over immense timescales. Red dwarfs, the smallest and longest-lived stars, will shine for 10 to 20 trillion years. The last red dwarf will sputter out around 100 trillion years from now, give or take. When it does, the age of starlight ends. The universe goes dark. By this time, galaxies will consist of dead stellar remnants, white dwarfs, neutron stars, and black holes, along with planets, asteroids, and cold gas. These objects will continue orbiting, gravitationally bound to their galaxies. But even these remnants won't last forever. Over timescales of 10-15 to 10-20 years, millions of billions of years, stars will gradually fall into central black holes or be ejected from galaxies through gravitational interactions. Eventually, galaxies will dissolve, their contents scattered or consumed by black holes. Planets will have separated from their dead stars long before this. Jupiter might orbit the Sun's white dwarf remnant for 10 to 20 years before being ejected. Earth, if it survives the Sun's red giant phase, would face a similar fate. By 10 to 30 years, galaxies as coherent structures will have largely evaporated. The universe will contain isolated dead stars, planets, and black holes, all drifting apart as space expands. But matter itself might not be stable. Theoretical physics suggests protons might decay with a half-life around 10 to 34 years, though this is highly uncertain and has never been observed. If proton decay occurs, then around 10 to 40 years, all ordinary matter, the atoms making up everything we know, will have decayed into lighter particles and radiation. Black holes, the last refuges of structure, will themselves evaporate through Hawking radiation. Stephen Hawking showed that black holes aren't truly black quantum effects, cause them to radiate particles, slowly losing mass. For solar mass black holes, evaporation takes about 10 or 67 years. Supermassive black holes at galactic centers take up to 100 years to evaporate completely. When the last black hole evaporates around 100 years from now, the universe will contain only dilute radiation and a thin soup of elementary particles, all drifting apart as space expands. Temperature will be a tiny fraction above absolute zero. No structure of any kind will exist. This is heat death, maximum entropy, thermal equilibrium at near absolute zero, all useful energy exhausted. The universe continues expanding forever, but nothing interesting happens. It's functionally dead, even though time continues. For any conscious beings existing in this universe, the implications are grim. Stars and planets hospitable to life exist only in a brief window of cosmic history, the first trillion years or so, less than 1/10,000,000th of the universe's ultimate lifespan. But perhaps heat death isn't the only possibility. If dark energy is more complex than a simple cosmological constant, other fates become possible, some even more disturbing. The Big Rip, when acceleration becomes catastrophic. Most models of dark energy have W greater than or equal to 1, meaning dark energy's density is constant, W sine 1, or decreases as the universe expands, W in 1. But theoretical possibilities exist where W is less than 1, called phantom energy. If W1, dark energy density, increases as the universe expands, this creates runaway acceleration with catastrophic consequences. Currently, dark energy accelerates cosmic expansion, but is far too weak to overcome gravity on smaller scales. It can't tear apart galaxy clusters, galaxies, solar systems, or planets. Its effects are noticeable only over billions of light years. But if dark energy density increases over time, it eventually becomes strong enough to overcome progressively stronger gravitational bonds. First, galaxy clusters are pulled apart, then galaxies, then solar systems, then planets, then molecules, then atoms, then atomic nuclei, and finally, space-time itself might be torn apart. This scenario is called the Big Rip, and it's as dramatic as it sounds. Here's a possible timeline if WW Chapter 1.5, phantom energy considerably stronger than currently observed. About 22 billion years from now, just 35 billion years after the Big Bang, only twice the universe's current age galaxy clusters are disrupted. Galaxies that are currently bound into groups fly apart as dark energy overwhelms their mutual gravity. About 60 million years before the end, the Milky Way is torn apart. Stars that have orbited the galactic center for billions of years are scattered into intergalactic space. Any civilization existing then would see their night sky gradually emptying as stars drift apart. About 3 months before the end, planetary systems are disrupted. Earth would be pulled away from the Sun. Both would continue existing briefly as isolated objects, but with no star nearby, Earth's surface would freeze solid within weeks. About 30 minutes before the end, planets and other solid objects are torn apart. The gravitational force holding Earth together can no longer overcome dark energy's disruptive force. The planet would fragment violently. About 19 seconds before the end, atoms are ripped apart. Electrons are stripped from nuclei. The chemistry that underlies life, thought, and all complex structure ceases to be possible. Finally, at the moment of the Big Rip, atomic far beyond the heat-death timescale. But we can't completely rule out phantom energy. Future precision measurements might reveal W is slightly less than 1, which would change the universe's ultimate fate from gradual heat death to violent destruction. There's another possibility. W might change over time. Dark energy could currently be a cosmological constant, but might transition to phantom energy in the distant future, or vice versa. Without understanding dark energy's fundamental nature, we can't predict its future behavior with certainty. The Big Crunch. Expansion reversed. Before the discovery of acceleration, many cosmologists expected the universe would eventually stop expanding and recollapse in a big crunch, the time-reversed version of the Big Bang. In this scenario, if the universe contained enough matter, its gravitational attraction would eventually overcome the expansion, bringing everything back together. The expansion would slow, stop, and reverse. Galaxies would begin approaching each other rather than receding. As the universe contracted, it would heat up, the reverse of how expansion causes cooling. Eventually, galaxies would collide and merge. Stars would be torn apart. Matter would be compressed to higher and higher densities and temperatures. Finally, everything would collapse into a singular point of infinite density and temperature, the Big Crunch, the universe's ultimate ending matching its beginning. Some theoretical models suggest the Big Crunch might trigger a new Big Bang, creating a cyclic universe that expands and contracts eternally. Each cycle might last hundreds of billions or trillions of years, with the universe expanding from a bang, reaching maximum size, contracting to a crunch, and bouncing into a new bang. This idea is appealing. It avoids the ultimate heat death and suggests the universe is eternal, having no true beginning or end, just endless cycles. However, the discovery of dark energy and accelerating expansion strongly disfavors the Big Crunch scenario, at least in the foreseeable future. Unless dark energy somehow weakens or reverses in the future, gravity will never overcome the acceleration to cause recollapse. Some theoretical models involve dark energy that eventually decays or transitions to attractive gravity, allowing a future big crunch. But current evidence gives no indication this will happen. The Big Crunch remains a theoretical possibility, but appears increasingly unlikely given what we know about dark energy. The universe seems destined for eternal expansion and eventual heat death rather than collapse. False vacuum decay, the ultimate phase transition. There's one more apocalyptic scenario worth discussing: vacuum metastability and false vacuum decay. This threat comes from quantum field theory and could happen at any moment without warning, destroying the universe as we know it. In quantum field theory, the vacuum empty space is associated with the ground state of quantum fields. Ideally, fields should be in their lowest possible energy state, called the true vacuum. But it's possible our vacuum is metastable, seemingly stable, but not truly in the lowest energy state. We might be in a false vacuum, separated from the true vacuum by an energy barrier, like a ball sitting in a small hollow on a hillside above a deeper valley. Quantum tunneling could allow the field to suddenly transition from false to true vacuum, like the ball spontaneously tunneling through the hill to reach the deeper valley. If this happens, a bubble of true vacuum would form and expand at the speed of light, converting false vacuum to true vacuum. Inside the bubble, physics would be different. Particle masses, force strengths, and perhaps even the number of spatial dimensions could change. Chemistry would work differently. Atoms might not be stable. Any structure existing in the false vacuum stars, planets, life would be destroyed or fundamentally altered. The bubble wall would be a boundary between our universe's physics and something completely different. It would expand unstoppably at light speed, eventually consuming the entire observable universe. Since it travels at light speed, we'd have no warning the bubble would arrive at the same moment we'd see it coming. Is our vacuum metastable? We don't know for certain. Calculations based on the standard model of particle physics, combined with measurements of the Higgs boson and top quark masses, suggest our vacuum might be metastable, though calculations are uncertain. If the vacuum is truly metastable, we can calculate the probability of decay. For reasonable assumptions, the expected lifetime is enormously far longer than the current age of the universe, perhaps 10 to 100 years or more. The probability of decay in any human lifetime, or even in the lifetime of the Sun, is negligibly small. But it's possible we're just lucky. A metastable vacuum could decay at any time, and even if the probability is incredibly tiny, over infinite future time, it becomes inevitable. False vacuum decay represents the ultimate black swan event, something that's probably not happening in the next billion years, but could in principle happen tomorrow with no warning. It's cosmically unlikely, but not impossible. Some physicists lose sleep over this. Others point out that worrying about something so improbable is irrational. We face countless more immediate threats that deserve our attention, but it's a sobering reminder that the universe's apparent stability might be temporary. The physics we know could be valid only in a metastable false vacuum, and the universe could undergo a phase transition to something utterly different whenever quantum chance dictates. Conclusion: accepting cosmic mortality. We've explored dark energy and the various ways the universe might end: heat death through eternal expansion, violent destruction in a big rip, collapse in a big crunch, or sudden annihilation through vacuum decay. Current evidence points most strongly to heat death, gradual expansion and cooling until all stars burn out, all structure dissolves, and the universe reaches maximum entropy, a cold, dark expanse where nothing interesting ever happens again. This isn't a comforting answer. We naturally hope for continuation, for meaning, for our actions to have lasting significance. But the universe doesn't care about our hopes. Reality is what it is, regardless of our preferences. There's a certain austere beauty in accepting the truth. Yes, everything will eventually end. Stars will die, galaxies will dissolve, even black holes will evaporate. All structure is temporary, all complexity ephemeral, all order ultimately yields to chaos and entropy. But that doesn't make existence meaningless. Meaning doesn't require permanence. A beautiful sunset is meaningful even though it lasts only minutes. A human life is meaningful even though it lasts only decades. Perhaps the universe is meaningful even though it lasts only trillions of years before sliding into heat death. We exist in a remarkably special time, the first tiny fraction of cosmic history when stars shine, when planets exist, when life is possible. We're living in the universe's youth, when it's still interesting, still capable of supporting complexity and consciousness. This should inspire wonder, not despair. We're witnessing the universe during its brief moment of glory before the long darkness. We should appreciate how improbable and precious this moment is. Dark energy ensures that complexity is temporary on cosmic scales. But it doesn't diminish the reality or significance of complexity while it exists. Life, thought, love, curiosity, discovery. These things are real and meaningful regardless of what happens trillions of years from now. And who knows, perhaps future discoveries will reveal possibilities we haven't imagined. Maybe advanced civilizations can somehow manipulate dark energy or access other universes. Maybe vacuum decay leads somewhere interesting rather than to destruction. Maybe the cyclic universe is real, and each big crunch triggers a new Big Bang with new opportunities for structure and life. We shouldn't let ignorance fuel false hope, but we should acknowledge that our understanding is incomplete. Dark energy itself was completely unexpected until 1998. Who knows what other surprises await? For now, we know the universe is accelerating toward an ultimately cold and empty fate. That's the best answer science can currently provide. It's not the answer we might wish for, but it's honest. And honesty about the universe's ultimate fate might help us appreciate the present. Every star, every planet, every life, every moment of consciousness represents temporary order carved from chaos, burning bright against the darkness, existing for a cosmically brief time before entropy claims everything. Make the most of this moment. The universe is mortal, but so is everything, and mortality doesn't diminish meaning, it concentrates it. We exist during the universe's brief flowering, when complexity is possible, when minds can contemplate cosmos. That's worth celebrating, even if it doesn't last forever. Perhaps especially because it doesn't last forever, the universe will end, but it hasn't yet. And right now, here, in this improbable pocket of complexity and consciousness, existence continues burning bright against the dark. For now, that's enough. Measuring the unmeasurable. How we study dark energy. Understanding dark energy requires measuring the universe's expansion history with extraordinary precision. How do astronomers accomplish this? The techniques are ingenious, each providing independent confirmation of acceleration. Type Ia supernovae remain the gold standard. These cosmic explosions reach similar peak brightnesses because they occur at a consistent mass threshold. By comparing apparent brightness to expected intrinsic brightness, astronomers calculate distance. By measuring redshift, how much light has stretched due to expansion, they determine how fast the universe was expanding when that light was emitted. The process is remarkably precise. Modern supernova surveys have measured hundreds of Type Ia supernovae spanning vast distances from nearby galaxies at redshifts around 0.01, representing light emitted mere millions of years ago, to distant galaxies at redshifts beyond 1.5, where we see the universe as it was over 9 billion years ago. This cosmic time machine reveals expansion history. Plotting distance versus redshift shows deviation from a coasting, matter-dominated universe. The deviation indicates acceleration, with dark energy becoming dominant about 5 billion years ago, coincidentally around the time Earth formed. But supernovae aren't the only method. The cosmic microwave background radiation from 380,000 years after the Big Bang provides complementary information. Tiny temperature fluctuations in this radiation reflect sound waves in the early universe's hot plasma. These acoustic oscillations imprinted a characteristic scale on the CMB. By measuring this scale and comparing it to the universe's current size, astronomers determined the geometry and composition of the universe. The data demand dark energy constituting about 68% of total energy, in remarkable agreement with supernova results. The CMB doesn't directly measure acceleration, but constrains dark energy's density precisely. Baryon acoustic oscillations offer yet another approach. The same sound waves visible in the CMB left imprints in the distribution of galaxies. Galaxies are slightly more likely to be separated by a specific distance, about 500 million light-years today, reflecting the sound wave scale from the early universe. By measuring this standard ruler at different cosmic epochs, astronomers can track how space has expanded over time. The technique requires mapping millions of galaxies in 3 dimensions, determining both their positions on the sky and their distances from redshifts. Multiple galaxy surveys, SDSS, DES, DESI, and others, have mapped cosmic structure across vast volumes, confirming accelerated expansion. Weak gravitational lensing provides additional evidence. Light from distant galaxies is bent by intervening matter, slightly distorting galaxy shapes. By statistically analyzing millions of galaxies, astronomers can map dark matter distribution and determine how structure has grown over time. Growth rate depends on dark energy. More dark energy means less gravitational clumping. Observations match predictions for a universe dominated by dark energy with W near 1. Combining these independent techniques, supernovae, CMB, BAO, lensing yields consistent results. Dark energy constitutes roughly 68% of cosmic energy. Its equation of state parameter W is very close to 1, within a few percent. If W varies with time, the variation is small. This concordance across multiple methods gives confidence in dark energy's reality despite its mysterious nature. We may not know what it is, but we're certain it exists. The coincidence problem. Why now? One of the most puzzling aspects of dark energy is timing. Why does it dominate the universe now, during the exact epoch when intelligent life exists to observe it? For most of cosmic history, dark energy was dynamically irrelevant. Immediately after the Big Bang, radiation dominated the universe's energy budget. As expansion stretched radiation wavelengths, radiation density decreased rapidly proportional to 1 over the universe's size, to the 4th power. After about 50,000 years, matter overtook radiation. For the next several billion years, matter both ordinary and dark-dominated cosmic dynamics. Dark energy was present but negligible compared to matter's density. But matter density decreases as the universe expands, proportional to 1 over volume or 1 over size cubed. Dark energy density, however, remains constant if W circa 1. Eventually, around 5 billion years ago, dark energy and matter density became comparable. Shortly thereafter, dark energy took over as the dominant component. Why is this transition occurring now? The universe is 13.8 billion years old. If we wait another 10 billion years, dark energy will be thousands of times more dominant than matter. If we go back 10 billion years, matter was thousands of times more dominant than dark energy. We exist during a transition period lasting perhaps 10 billion years, a narrow window in cosmic history. Before this window, matter dominated and dark energy was negligible. After this window, dark energy will dominate completely and matter will be negligible. This seems like an odd coincidence. Of all possible epochs in cosmic history to be born, why do we find ourselves during the transition? Some argue this is anthropic reasoning. Life requires billions of years for stars to form, planets to cool, evolution to produce complexity. Intelligent observers necessarily exist during later cosmic epochs, and during later epochs, dark energy inevitably becomes important because matter dilutes while dark energy doesn't. So perhaps there's no coincidence at all. We observe dark energy becoming dominant because we exist late enough in cosmic history for intelligence to evolve, and by that time, dark energy naturally becomes important. Others find this unsatisfying. It doesn't explain why dark energy's density is the specific value it is, why not 1,000 times larger or smaller. And it doesn't explain why dark energy was so perfectly subdominant for most of cosmic history before recently taking over. Some physicists propose quintessence models with tracking behavior. The dark energy field's evolution is linked to matter density, keeping them comparable through cosmic history before dark energy takes over. This would make the coincidence less sharp. But no compelling physical mechanism for tracking has been established. And tracking models must still explain why dark energy density is the specific value observed. The coincidence problem remains unresolved, another mystery surrounding dark energy's nature and role in cosmic evolution. The Boltzmann brain problem, consciousness from chaos. Dark energy creates a bizarre philosophical problem called Boltzmann brains, named after Austrian physicist Ludwig Boltzmann, who first explored related ideas about entropy and probability. In a heat-death universe, expanding eternally with constant dark energy density, empty space persists forever. Quantum fluctuations constantly occur. Virtual particles pop in and out of existence throughout space and time. Most fluctuations are small and local, but over infinite time, any fluctuation that's possible, no matter how improbable, will eventually occur somewhere. This includes large fluctuations that spontaneously create complex structures, including brains with false memories of having lived full lives. These Boltzmann brains would be vastly more common than real brains evolved in planets around stars. Real brains require stars to form, planets to cool, life to evolve, an incredibly improbable sequence. Boltzmann brains just require quantum fluctuations large enough to spontaneously assemble brain-like structures. In an eternal heat-death universe, almost every conscious observer would be a Boltzmann brain, a disembodied brain floating in space with false memories, existing briefly before dissociating back into chaos. Real evolved brains like ours would be vanishingly rare. If Boltzmann brains dominate, then by probability you're almost certainly a Boltzmann brain. Your memories of reading this are false, spontaneously generated. You'll cease to exist in moments. The universe around you doesn't actually exist. This conclusion is absurd, a reductio ad absurdum suggesting something has gone wrong in the reasoning. But where? Some argue the problem shows heat-death scenarios are wrong. Perhaps the universe doesn't expand forever? Perhaps vacuum decay or some other process terminates existence before Boltzmann brains dominate. Others suggest Boltzmann brains are impossible quantum fluctuations, can't actually create brains, or consciousness requires more than just instantaneous brain structure. But this seems like wishful thinking without strong theoretical justification. A third approach involves the anthropic principle and multiverse. If we live in a multiverse, perhaps we should count observers properly weighted across all universes, not just within one eternal universe. This might save us from being Boltzmann brains, though the details are murky. The Boltzmann brain problem highlights deep issues about probability, consciousness, and cosmology. It's not clear what the correct resolution is, but it suggests our understanding of eternal universes and entropy remains incomplete. Modified gravity. What if Einstein was wrong? Nearly all dark energy research assumes general relativity is correct and attributes acceleration to some new form of energy. But there's an alternative. Perhaps gravity itself behaves differently on cosmic scales. General relativity has been tested extensively in the solar system and in binary pulsars. It works extremely well on these scales. But the largest scales, tens of millions to billions of light years, are poorly tested. Maybe Einstein's equations need modification at cosmic distances. Modified gravity theories, generically called modified Newtonian dynamics, or MOND, when applied to galaxy scales, suggest that gravitational attraction might change character on large scales or at small accelerations. If true, this could potentially explain both dark matter and dark energy without requiring new substances. Perhaps galaxies rotate faster than visible matter suggests, not because invisible dark matter is present, but because gravity works differently in low acceleration regimes. Perhaps the universe accelerates not because dark energy pushes, but because gravity on cosmic scales differs from Einstein's predictions. Numerous modified gravity theories have been proposed: scalar tensor theories, FR gravity, DGP models, and others. Each modifies Einstein's equations in different ways while trying to maintain agreement with solar system tests. The challenge is making modified gravity work. Most proposed modifications either conflict with observations or require fine-tuning that's as contrived as explaining dark energy directly. Many modified gravity theories predict gravitational wave speeds differing from light speed, ruled out by 2017 observations of a neutron star merger where gravitational waves and gamma rays arrived within 2 seconds after traveling 130 million light-years. A few models survive observational constraints, but they're complicated and arguably less elegant than simply accepting dark energy as a real substance. Occam's razor doesn't clearly favor modified gravity over dark energy. Moreover, modified gravity struggles to explain certain cosmological observations. The cosmic microwave background and large-scale structure formation fit beautifully with dark matter and dark energy in Einstein's gravity. Modified gravity models have difficulty matching these observations without adding dark components anyway. Most physicists favor dark energy over modified gravity, but the possibility remains open. Perhaps gravity at cosmic scales harbors surprises we haven't discovered. Future tests, especially precision measurements of gravitational waves and structure growth, might reveal subtle deviations from Einstein's theory. For now, general relativity plus dark energy remains the standard model. But science advances by questioning assumptions, so modified gravity research continues, probing whether our gravitational understanding is truly complete. Life in an accelerating universe. Long-term prospects. What does dark energy mean for the long-term future of life and intelligence in the universe? In the near term, the next billions of years, dark energy changes little. Stars continue forming, planets continue orbiting, life continues evolving. Acceleration is noticeable only on the largest scales, affecting clusters of galaxies, but not individual galaxies or solar systems. But over tens of billions of years, dark energy's effects become profound. Distant galaxies disappear beyond the cosmic horizon, carried away by accelerating expansion. The observable universe shrinks. Counterintuitively, in an expanding universe, we'll eventually see less as distant regions accelerate beyond light's ability to reach us. Any civilization existing 150 billion years from now would see a very different universe. Most galaxies would have vanished. The cosmic microwave background would be undetectable. Evidence for the Big Bang would be lost. Astronomers in that era might incorrectly conclude they live in an eternal, static universe containing only their local group of gravitationally bound galaxies. This has happened already in reverse. Ancient civilizations existed in a pre-telescope era, unable to see distant galaxies, reasonably believing their local patch represented all existence. We are fortunate to live during a window when the universe's true scope and history are observable. But life faces more serious challenges over trillions of years. Star formation will cease when gas is exhausted or expelled. No new suns will ignite after perhaps 100 trillion years. Existing stars will burn out over immense timescales, leaving darkness. Advanced civilizations might adapt, harvesting energy from dying stars, from black holes, perhaps even from dark energy itself, if that's possible. They might create artificial environments independent of natural stars and planets. But thermodynamics is inescapable. Entropy increases, usable energy decreases, order gives way to chaos. Even the most advanced civilization cannot evade heat death in a universe dominated by dark energy. Some speculate about escaping to other universes through wormholes or some other mechanism. Others imagine creating baby universes or manipulating vacuum decay to survive phase transitions. These are wild speculations with no theoretical foundation, but they're not obviously impossible. More sobering is recognizing that intelligence might be a brief flowering in cosmic history. We exist during a special epoch, after simple matter has had time to organize into complexity, but before heat death claims everything. This window perhaps spans 100 trillion years, less than 1/10,000,000th of the universe's ultimate lifespan. If we're typical intelligent observers, most other civilizations exist during this window too, scattered across space and time. And like us, they're contemplating their cosmic mortality, knowing their existence is temporary on the longest scales. This should motivate urgency. We have a limited time, astronomically long by human standards, but finite nevertheless, to accomplish whatever we believe is worth accomplishing before heat death erases all structure. Perhaps the most important goal is simple: continue existing, continue thinking, continue expanding knowledge and complexity for as long as physics permits. Every moment of consciousness, every discovery, every creative act represents a temporary victory of order over entropy, meaning over chaos. Make those moments count. The universe won't last forever, but we're here now, and now is all that ultimately matters. Conclusion: the weight of knowledge. We began with a simple question: what will happen to the universe? The answer, as best we can determine, is that dark energy will drive eternal expansion, leading eventually to heat death. A cold, dark, empty cosmos where all structure has dissolved and nothing interesting remains. This isn't speculation or pessimism. It's our best scientific understanding based on decades of observations and theoretical work. Dark energy exists, acceleration is real, and the implications are inescapable. Some find this knowledge depressing. The universe is mortal, complexity is temporary. Everything we know and love will ultimately end in darkness and cold. What's the point if it's all meaningless in the end? But knowledge of mortality doesn't erase meaning. It concentrates it. We don't dismiss human accomplishments because humans are mortal. We don't ignore beauty because it's temporary. Why should cosmic mortality matter differently? The universe won't last forever. Neither will we. Neither will Earth, the Sun, the Milky Way, or anything else. But they exist now, and now is real and meaningful regardless of ultimate fate. There's even a certain nobility in accepting the truth. We're intelligent enough to foresee our own cosmic ending, brave enough to face it without comforting delusions. That's worth something. And who knows what future discoveries await. Dark energy itself was unknown until 1998, a quarter century ago. Physics has surprised us repeatedly. Perhaps it will again. Maybe dark energy will prove different from what we currently think, with implications we haven't imagined. Maybe advanced civilizations can manipulate fundamental forces in ways we don't understand. Maybe the multiverse exists and consciousness can somehow access alternate realities. Or maybe not. Maybe heat death truly is inevitable and all we can do is make the most of our brief moment in the sun before darkness claims everything. Either way, we should appreciate what we have. We exist during a remarkable era, the universe's youth, when stars shine and complexity flourishes. We have perhaps trillions of years before heat death, an incomprehensibly long time by human standards, though brief in cosmic context. Make use of this time. Learn, create, explore, love, think, wonder. Expand the boundaries of knowledge and complexity. Push back against entropy as far as physics allows. Dark energy ensures the universe will end, but it hasn't ended yet. And in the meantime, here we are, conscious beings capable of comprehending cosmos, of understanding our own mortality on the grandest possible scale. That's extraordinary. That's precious. That's worth celebrating. The universe is mortal, so celebrate it while it lives. Recognize the improbability and beauty of existence during this brief cosmic moment when complexity is possible, when minds can contemplate the infinite. Dark energy will have the final word. But for now, for this moment, the word is ours. And that's enough. The Lambda CDM model, our standard cosmology. The prevailing model of the universe, developed over decades and supported by multiple lines of evidence, is called Lambda CDM, named for dark energy, lambda, Einstein's cosmological constant symbol, and cold dark matter. This model describes a universe that's spatially flat, meaning parallel lines remain parallel, and Euclidean geometry applies on large scales. It contains about 68% dark energy, 27% dark matter, and 5% ordinary matter. The universe began 13.8 billion years ago in a hot, dense state and has been expanding ever since, with the expansion recently accelerating. Lambda CDM successfully explains numerous observations. It predicts the cosmic microwave background's temperature fluctuations with stunning accuracy. It explains how galaxies and galaxy clusters formed through gravitational growth of tiny initial density variations. It matches the abundance of light elements like hydrogen, helium, and lithium produced in the first minutes after the Big Bang. The model has 6 fundamental parameters that must be measured from observations. The Hubble constant, describing expansion rate, dark energy density, dark matter density, ordinary matter density, the amplitude of initial density fluctuations, and their scale dependence. Multiple independent measurements constrain these parameters consistently, with precision often reaching 1 or 2%. But Lambda CDM is descriptive rather than explanatory. It tells us how much dark energy and dark matter exist, but not what they are. It's like knowing water comprises 2 parts hydrogen and 1 part oxygen without understanding atomic structure. We have the recipe, but not the underlying theory. The search for deeper understanding drives cosmology. What is dark matter? What is dark energy? Are they fundamental substances or symptoms of incomplete understanding? Lambda CDM can't answer these questions. It merely parameterizes our ignorance precisely. Still, Lambda CDM represents enormous progress. A century ago, we didn't know other galaxies existed. 50 years ago, we didn't know about dark matter or dark energy. Today, we have a detailed quantitative model matching observations across vast ranges of scale and time. That's remarkable even if major mysteries remain. Science advances by transforming vague questions into precise problems, and Lambda CDM has transformed cosmology from speculation into precision science. The Hubble tension, a crisis in cosmology? Despite Lambda CDM's success, a troubling discrepancy has emerged. Different methods for measuring the universe's expansion rate give inconsistent results, a problem called the Hubble tension. The Hubble constant quantifies how fast the universe expands, specifically how much faster distant galaxies recede for each additional megaparsec of distance. A galaxy 1 megaparsec away recedes at Hi0 kilometers per second, where Hi0 is the Hubble constant. Measurements from the cosmic microwave background, combined with Lambda CDM predictions, give Hi0 equal to about 67 kilometers per second per megaparsec. But measurements using distance ladders calibrated distances to nearby galaxies, Cepheid variable stars, and type Ia supernovae give Hi0 equal to about 73 kilometers per second per megaparsec. This 9% difference might not sound significant, but both measurements claim precision better than 2%. They disagree by more than 5 standard deviations in statistical terms, a highly significant discrepancy unlikely to be mere chance. What explains the tension? Several possibilities exist. First, systematic errors. Perhaps one or both measurement methods has unrecognized problems. Maybe dust dims supernovae more than assumed. Maybe Cepheid calibrations have subtle biases. Maybe the CMB analysis makes incorrect assumptions. Both camps have checked extensively for errors and are confident their results are robust. But systematic errors can be subtle and difficult to identify. Second, new physics. Perhaps Lambda CDM is incomplete. Maybe dark energy evolves differently than assumed, or extra-relativistic particles existed in the early universe, or gravity behaves unexpectedly. Any of these could alter predicted expansion rates. Some physicists propose dark energy had different properties before and after acceleration began, creating the tension. Others suggest additional neutrino species or early dark energy temporarily boosted expansion. Many models have been proposed, none entirely satisfactory. Third, local effects. Perhaps we live in a cosmic void region with below-average density. Local expansion would differ from the universal average, potentially explaining the discrepancy. But the local void would need to be enormous, hundreds of millions of light-years across, and observations don't clearly support such a large underdensity around us. The Hubble tension remains unresolved despite years of effort. It could be a harbinger of new physics beyond Lambda CDM, or it could evaporate as measurements improve and errors are identified. Either outcome would be significant. Discovering new physics would revolutionize cosmology. Resolving the tension within Lambda CDM would confirm our model is robust, even under intense scrutiny. Time will tell. Multiple upcoming surveys, JWST observations, Euclid satellite measurements, Vera Rubin Observatory data will provide fresh perspectives. By decade's end, the Hubble tension should be resolved one way or another. The vacuum catastrophe. Why is dark energy so small? Earlier, we discussed the cosmological constant problem, the fact that quantum field theory predicts vacuum energy 10 or 120 times larger than observed. This is arguably the worst theoretical prediction in science history and represents a profound gap in our understanding. Let me explain this problem more deeply because it's central to dark energy's mystery. Quantum field theory describes particles as excitations in quantum fields pervading all space. Even in empty space, quantum fields have zero-point energy. They're never completely still due to Heisenberg's uncertainty principle. For each quantum field, this zero-point energy contributes to vacuum energy density. There are dozens of quantum fields in the standard model fields for electrons, quarks, photons, gluons, Higgs bosons, and so on. Each contributes its zero-point energy. When you calculate the total using standard quantum field theory techniques, you get an enormous number. The calculation is technically intricate, involving integrals over all possible wavelengths and energies up to some cutoff scale. But the upshot is clear. Theory predicts vacuum energy density around 10⁻113 joules per cubic meter. Observations show dark energy density is about 6 x 10⁻10 joules per cubic meter, smaller by a factor of about 10⁻123. This is like predicting someone's height as 10⁻23 times the diameter of the observable universe and being off by that factor. It's not just wrong, it's spectacularly, absurdly wrong. Why is the vacuum energy so small? No one knows. Several possibilities exist, none satisfying. First, maybe quantum field theory breaks down when calculating vacuum energy. Perhaps there's a subtlety in applying quantum theory to gravitational systems. But what subtlety, and why does it give exactly the right small answer? Second, maybe there's a symmetry principle that cancels most vacuum energy. Supersymmetry, a hypothetical symmetry relating matter particles to force particles, would partially cancel vacuum energy, but not nearly enough. And supersymmetry hasn't been detected at particle accelerators despite extensive searches. Third, maybe anthropic selection in a multiverse explains the small value. If vacuum energy varied across bubble universes, only universes with small values would develop structure and produce observers. We exist in a low vacuum energy bubble because that's the only type where life is possible. This anthropic explanation is controversial. It gives up on finding a dynamical mechanism, accepting that the value is environmentally determined. Many physicists find this unsatisfying, but others argue it might be correct. Fourth, maybe our vacuum is metastable, as discussed earlier, and the true vacuum has much lower energy, perhaps exactly zero. We're stuck in a false vacuum with small but non-zero cosmological constant. But this doesn't really solve the problem, it just pushes it back. Why does the false vacuum have exactly the observed small positive value rather than some other value? The vacuum catastrophe remains one of theoretical physics' deepest mysteries. It suggests our understanding of quantum field theory, gravity, or both is fundamentally incomplete. Solving it might require revolutionary new physics. Until we understand why vacuum energy is so small, we can't claim to understand dark energy. We measure it, we model its effects, but we don't understand its origin or nature. That's an enormous gap in our knowledge. Primordial dark energy. Did it drive inflation? Dark energy's properties, nearly constant density and negative pressure causing accelerated expansion, resemble those of the inflaton field believed to have driven cosmic inflation in the universe's first fraction of a second. During inflation, the universe expanded exponentially, growing from subatomic size to macroscopic size in about 10 to 35 seconds. This solved numerous cosmological problems and left observable imprints matching current measurements. The inflaton was a quantum field with potential energy dominating its kinetic energy, creating a temporary state of dark energy that drove violent expansion. Eventually, the inflaton decayed, its energy converting to radiation and matter, ending inflation and beginning the hot Big Bang phase. Could modern dark energy be related to primordial inflation? Perhaps it's the same field or a similar field with different properties now compared to then. Some physicists propose quintessential inflation models, where a single field drives both early inflation and late-time acceleration. The field starts high on its potential during inflation, rolls down, rapidly causing exponential expansion, overshoots the minimum, oscillates while reheating the universe, then slowly rolls toward its minimum billions of years later, causing modern acceleration. This is elegant one field explaining two unexplained phenomena, but quintessential inflation models are highly constrained by observations and require carefully tuned potentials to match both inflationary predictions and dark energy properties. Other researchers suggest no direct connection. Inflation and dark energy involve different physics at different energy scales. The coincidental similarity might be just that, coincidence, or perhaps a hint of some deeper principle we don't yet understand. Either way, the comparison is instructive. Both inflation and dark energy involve periods when vacuum energy or field energy dominates cosmic dynamics, driving accelerated expansion. Both require theoretical components beyond ordinary matter and known forces. Perhaps this teaches us that accelerated expansion is more natural or common than we initially thought. Maybe the universe's default state is acceleration, with matter-dominated deceleration being the unusual interlude. We're witnessing a return to cosmic normalcy after a temporary period of slowing. Or perhaps we're reading too much into superficial similarities. Inflation lasted 10 or 35 seconds. Modern acceleration began 5 billion years ago and continues indefinitely. The energy scales differ by factors of 10^120. They might be completely unrelated phenomena. Time and better theoretical understanding will clarify whether inflation and dark energy are connected or merely analogous. Either answer would teach us something profound about how the universe works. Beyond Einstein, quantum gravity and dark energy. Dark energy might be intimately connected to the biggest unsolved problem in theoretical physics: quantum gravity unifying quantum mechanics and general relativity. Quantum mechanics governs the microscopic world with stunning accuracy. General relativity governs gravity and space-time with equal success. But the theories are mathematically incompatible. Attempts to apply quantum mechanics to gravity produce infinite nonsensical answers. The theory breaks down at very high energies or small distances. This isn't just academic. At the Planck, scale energies around 10^19 GeV or distances around 10^35 meters quantum effects become comparable to gravitational effects. Space-time itself should fluctuate quantum mechanically. Black holes evaporate through quantum processes. The Big Bang singularity requires quantum gravity to describe properly. We need a quantum theory of gravity, but despite decades of effort, none has been fully developed and tested. String theory and loop quantum gravity are leading candidates, but neither has made definitive testable predictions confirmed by observation. Dark energy might provide clues about quantum gravity. The cosmological constant is a property of space-time itself. Einstein's equations allow it as a fundamental constant of nature. Its value might be determined by quantum gravity, by whatever theory ultimately reconciles quantum mechanics with general relativity. Some quantum gravity approaches suggest space-time has discrete structure at tiny scales. Space and time come in minimal units rather than being infinitely divisible. This discreteness might affect vacuum energy calculations, potentially explaining why the observed value differs so dramatically from naive quantum field theory predictions. Alternatively, quantum gravity might reveal that our concept of vacuum is wrong. Perhaps what we call empty space isn't the ground state at all. Perhaps there's a deeper level of reality where our vacuum is an excited state, and dark energy reflects the difference between our vacuum and the true ground state. These are speculations, but they highlight how dark energy connects to fundamental physics. Understanding it might require solving quantum gravity. Conversely, solving quantum gravity might automatically explain dark energy as a consequence of deeper theory. This connection between cosmology and fundamental physics is one of modern science's exciting frontiers. The universe's largest scale behavior, dark energy driving cosmic acceleration, might be determined by physics at the smallest conceivable scales, the Planck length, where quantum gravity matters. That's both humbling and thrilling. It means we must understand both extremes, cosmic and quantum too, claim a complete understanding of reality. Neither alone suffices. They're interconnected in ways we're still discovering. Living with uncertainty, the scientific method at the edge. After this deep dive into dark energy, you might feel frustrated. We've identified a phenomenon dominating the universe, yet admitted we don't know what it is. We've described various scenarios for cosmic fate while acknowledging uncertainty. This is science operating at its frontier. Not everything is known. Not everything is certain. That's okay. That's how discovery works. Science isn't about having all the answers. It's about asking questions systematically, following evidence wherever it leads, and honestly acknowledging what we don't know while working to expand knowledge. Dark energy exemplifies frontier science. We have excellent observations revealing its existence and properties. We have theoretical frameworks attempting to explain it. We have predictions about cosmic fate that follow from different assumptions, but we lack definitive understanding of its fundamental nature. This is actually exciting, not disappointing. It means there's more to discover. The universe still holds secrets. Future observations might reveal answers we haven't imagined. Consider how far we've come. A century ago, we didn't know galaxies existed beyond our own. 70 years ago, we didn't know about the Big Bang. 50 years ago, we didn't know about dark matter. 25 years ago, we didn't know about dark energy. Each discovery transformed cosmology. Each revealed the universe was stranger and more wonderful than previously thought. Who knows what the next 25 years will bring? Maybe we'll detect dark energy directly in laboratory experiments. Maybe we'll discover it's a new quantum field with measurable properties. Maybe we'll find it's really modified gravity. Maybe we'll discover something completely unexpected that makes current mysteries evaporate. Or maybe dark energy will remain mysterious, forever beyond direct detection, knowable only through its cosmic effects. Even then, we'll keep learning, refining measurements, testing theories, pushing toward deeper understanding. That's the scientific method. Observe, hypothesize, predict, test, repeat. Sometimes progress is slow. Sometimes mysteries persist for decades. But the method works. It's delivered essentially everything we know about the universe beyond everyday experience. Living with uncertainty is part of science. So is maintaining intellectual humility while being confident in what evidence does establish. We know dark energy exists. We know it's causing acceleration. We know it determines cosmic fate. Those aren't speculations, they're established facts. What we don't know is dark energy's fundamental nature. That's the next challenge, the next frontier, and confronting it honestly, acknowledging both what we know and what we don't, is the only path forward. Conclusion: mortal universe, mortal us. We've explored one of cosmology's deepest mysteries. Dark energy, the mysterious force driving the universe's accelerating expansion and determining its ultimate fate. The evidence is clear. Observations from multiple independent sources, supernovae, cosmic microwave background, galaxy distributions, gravitational lensing, all point to the same conclusion. Dark energy is real, it dominates the universe, and it ensures ongoing acceleration toward eventual heat death. The theory is incomplete. We don't know what dark energy fundamentally is. Is it Einstein's cosmological constant, quintessence, modified gravity, something else? The answer remains unknown despite decades of research. The implications are stark. The universe won't last forever in any form we'd recognize as interesting. Stars will die, galaxies will dissolve, structure will fade, and heat death will claim everything. This is as close to certain as cosmology gets, barring revolutionary discoveries. How should we feel about this? Depressed? Liberated? Motivated? Indifferent? Perhaps all of the above in different moments. Yes, it's sobering to know existence is temporary on cosmic scales. Everything we know and love will ultimately be erased. The heat death of the universe is coming, inexorable and unstoppable. But that's always been true, even before we understood dark energy. Nothing lasts forever. Not stars, not galaxies, not universes. Permanence was never on offer. Dark energy just clarifies the specific mechanism and timeline matters. Heat death is trillions of years away, unfathomably longer than humans have existed, longer than Earth has existed, longer than the sun will shine. By any reasonable standard, that's effectively forever. We have time, not infinite time, but more time than we can meaningfully contemplate. Whatever we hope to accomplish, exploring the cosmos, preserving knowledge, creating beauty, expanding consciousness, trillions of years provide ample opportunity. Perhaps more importantly, cosmic mortality mirrors personal mortality. You will die. I will die. Everyone you love will die. Yet we don't therefore conclude life is meaningless. We find meaning in the living, not in eternal preservation. The same applies cosmically. The universe won't last forever, but it exists now, and existence itself is worthy of appreciation. Every star, every galaxy, every moment of complexity represents improbable order carved from chaos, burning bright against the dark. Dark energy ensures this won't last forever, but forever is overrated anyway. What matters is now, this moment, this existence, this improbable universe that gave rise to stars and planets and life and minds capable of understanding their own cosmic mortality. That's extraordinary. That's precious. That's worth celebrating, even knowing it's temporary. So face the future honestly. The universe is dying, slowly but inevitably, driven toward heat death by dark energy we don't understand. That's the truth, as best we know it. But face the present with joy. Here we are, conscious beings on a planet orbiting a star in a galaxy filled with billions of stars, in a universe containing billions of galaxies, existing during a cosmically brief window when complexity flourishes and minds can contemplate cosmos. This moment won't last forever. Nothing does, but it's happening now, and now is real, and that's enough. The universe is mortal. So are we. Let's make the most of the time we have. Dark energy will have the final word. But for now, the word is ours. Speak it well. The cosmic calendar, our place in time, To truly appreciate dark energy's significance for cosmic fate, it helps to place ourselves in the universe's timeline. Imagine compressing all of cosmic history into a single year, the cosmic calendar. The Big Bang occurs at the stroke of midnight on January 1st. The universe is born, incredibly hot and dense, beginning its expansion that continues to this day. For the first months, little happens from a human perspective. The universe expands and cools. Hydrogen and helium form in the first minutes. The cosmic microwave background emerges after 380,000 years, mid-January on our calendar. First stars ignite perhaps 100 million years after the Big Bang late January or early February. These are massive, short-lived stars that quickly explode as supernovae, enriching space with heavier elements. Galaxies form throughout February and March, coalescing from slight density variations in the early universe. Dark matter's gravity pulls ordinary matter together, forming the large-scale structure we see today. Our Milky Way galaxy forms around early spring. The universe is now several billion years old, but still young, with most cosmic history ahead. The Sun and Earth form on September 2nd, about 4.6 billion years ago, in real time. More than two-thirds of cosmic history has elapsed before our solar system exists. Life emerges on Earth shortly thereafter. Early September. Simple, single-celled organisms dominate for months. Complex life doesn't appear until late November. Dinosaurs roam in late December and go extinct on December 26th. Modern humans appear at 11:52 p.m. on December 31st, just 8 minutes before midnight. All of recorded human history occupies the final minute. The scientific revolution occurs in the last second, the discovery of dark energy. 1998 happens in the last tenth of a second before midnight. We've known about the universe's accelerating expansion for less than an eye blink of cosmic time. Now consider the future. If the first cosmic year brought us from Big Bang to today, what about the second year? The third? The trillionth? On this scale, stars will continue forming well into the next several million cosmic years. The Milky Way and Andromeda will merge after about 15 cosmic years. The last stars will form after about 360,000 cosmic years. Heat death, when the last black holes evaporate, occurs after roughly 35 trillion cosmic years. If we compress all time from Big Bang to heat death into that single year, human existence occupies literally less than an instant. We exist in the first microsecond of the first day of a process spanning eons, yet we're privileged. We exist during the only period when the universe is interesting, when stars shine, when complexity flourishes, when consciousness can emerge. The vast majority of cosmic history, both past and future, is comparatively barren. We are cosmically young, but not too young. We exist after enough time has passed for heavy elements to form, for planets to cool, for life to evolve, but early enough that stars still shine and the universe remains hospitable. This temporal sweet spot might be rare. Most of cosmic time is either too early, no heavy elements, no planets, or too late, no stars, no energy. The window for complexity is brief. Maybe 1 trillion years from first stars to last, less than 1/10,000,000th of the universe's ultimate lifespan. We're alive during that window. Against tremendous odds, through remarkable fortune, we exist at exactly the right time. Appreciate that improbability. Don't waste it. The philosophy of cosmology, meaning in a dying universe. Dark energy raises profound philosophical questions about meaning, purpose, and significance in a universe destined for heat death. If everything ultimately ends, if all structure dissolves, if the universe's final state is cold, dark emptiness, then in what sense does anything matter? Are our lives, our civilizations, our entire existence ultimately pointless? The 19th century philosopher Arthur Schopenhauer would have loved dark energy. He argued existence was fundamentally suffering and meaninglessness, that striving was futile because death awaits everyone. Cosmic heat, death provides the ultimate vindication, not just individual death, but universal death, the erasure of everything that ever existed or mattered. But this is too pessimistic. Meaning doesn't require permanence. Consider a beautiful sunset. It lasts minutes, then fades. Does its transience make it meaningless? Of course not. The sunset is meaningful precisely because it's temporary. Its fleeting beauty concentrates attention and appreciation. The same applies to life. A human life spans decades, a cosmic eye blink. Does this make it meaningless? No one thinks so. We find tremendous meaning in relationships, achievements, experiences, and growth, despite knowing they're temporary. Why should cosmic scales differ? Yes, the universe will end, but that's trillions of years away. In the meantime, stars shine, planets orbit, life evolves, minds think. These things are real and meaningful regardless of ultimate fate. Some philosophers argue meaning requires transcendence, that significance requires existence beyond death, whether through souls, heaven, or other forms of persistence. Cosmic heat death seems to foreclose even hypothetical transcendence. When the universe dies, everything dies with it. But perhaps transcendence is overrated. Perhaps meaning inheres in the process, the living, the experiencing, not in eternal preservation. A song is meaningful while it plays, a story while it's told, a life while it's lived. When they end, they don't retroactively become meaningless. Moreover, we affect the future, even if that future is finite. Actions now influence tomorrow, next year, next century, next millennium. The chain of causation extends forward, shaping what happens even if heat death eventually claims everything. Your choices matter. They determine your life's trajectory and influence others' lives. Those others influence still others, and ripples propagate forward through time. That you'll eventually die doesn't negate your impact. That the universe will eventually die doesn't negate civilization's impact. Some find solace in legacy, leaving something behind that outlasts individual existence. Children, creations, contributions to knowledge, these provide symbolic immortality, persistence beyond personal death. But heat death threatens even legacy. If all structure ultimately dissolves, if no records survive, if no minds exist to remember, then doesn't everything ultimately vanish without trace? True, but again, does this matter? Legacy is about influence on the future that exists, not eternal preservation. If your actions positively shape the next 1,000 years, that's significant regardless of what happens thereafter. Perhaps the deepest question is whether the universe needs purpose. We evolved to seek purpose. It's adaptively useful for intelligent social animals. But the universe isn't obligated to provide cosmic purpose. It just is. Dark energy teaches this clearly. The universe wasn't designed for us, doesn't care about us, and will continue long after we're gone. Its fate is determined by physics, not by meaning or purpose we'd prefer. That's liberating, not depressing. We are free to create our own meaning without needing cosmic validation. Our lives matter because we decide they matter, because we value them and each other, not because the universe endorses our significance. Existentialist philosophers like Sartre and Camus emphasized this. We're radically free to define our own meaning in an indifferent universe. Dark energy makes the universe's indifference explicit, but the philosophical challenge remains the same. Create meaning, live authentically, Value what deserves valuing. Act ethically. Pursue knowledge and beauty and love. Not because the cosmos demands it, not because rewards await after death, but because these things are worthwhile in themselves, here and now, regardless of ultimate fate. The universe is dying. That's physics. But physics doesn't determine what matters to conscious beings during their brief existence. We do. And we can choose to make existence meaningful despite its temporariness, or perhaps because of it. That's the real lesson of dark energy and cosmic mortality. Not despair, but urgent appreciation. Not nihilism, but existential freedom. Not meaninglessness, but the responsibility to create meaning in the time we have. The universe won't last forever. Neither will we. Make it count anyway. That's not just good philosophy. It's the only philosophy that makes sense when you truly understand our cosmic situation. The final word: beauty in truth. We've journeyed from Edwin Hubble's discovery of cosmic expansion through the shocking revelation of acceleration into the deep mysteries of dark energy and the various scenarios for the universe's ultimate fate. The conclusion is clear. Dark energy drives accelerated expansion, and unless something unexpected happens, the universe is headed toward heat, death, eternal expansion, and cooling, until all structure dissolves into maximum entropy. This isn't comforting. It's not the story we might wish were true, but it's the story the evidence tells, and there's profound beauty in confronting truth honestly, even when truth is uncomfortable. Science has repeatedly revealed the universe to be larger, older, stranger, and more indifferent than humans naturally assume. Each discovery diminishes our cosmic significance while expanding our understanding. Copernicus showed Earth isn't the center of the universe. Darwin showed humans weren't specially created. Hubble showed our galaxy is one among billions. And dark energy shows even the universe itself is mortal, destined for eventual death. Each revelation was initially disturbing, each ultimately enriched rather than impoverished human understanding. Losing false certainty about our cosmic importance freed us to understand reality as it actually is, not as we'd prefer it to be. Dark energy continues this tradition. Yes, it's unsettling to know the universe will die, but knowing this is preferable to comforting delusions. Truth has intrinsic value, even when truth hurts, and there's beauty in the science itself. The observations connecting distant supernovae to cosmic fate, the mathematics describing space-time curvature and expansion, the theoretical frameworks attempting to explain dark energy's nature, the careful reasoning from evidence to conclusion. These represent human intelligence at its finest, asking deep questions, gathering evidence, following logic wherever it leads, and honestly reporting conclusions even when they're not what we'd hoped for. That's noble. That's worthy of respect and celebration. We're clever enough to foresee our cosmic ending, brave enough to face it without illusion. That counts for something. Moreover, understanding dark energy enables appreciation of our cosmic moment. We exist during a brief window when complexity flourishes, when minds can contemplate reality, when the universe is young and interesting and beautiful. Trillions of years from now, the universe will be dark and cold and empty, but it's not now. Now, stars shine, galaxies spiral, planets orbit, life thinks. And understanding why this won't last forever helps us appreciate that it's happening at all. So the final word is this: yes, dark energy will ultimately erase everything, but that's trillions of years away, and in the meantime, here we are, conscious beings capable of understanding our own cosmic mortality. That's extraordinary. That's precious. That makes this moment rare and valuable beyond measure. The universe is dying slowly. We're dying faster, Neither fact negates the significance of existence while it occurs. Dark energy determines cosmic fate, but we determine what our brief moment means. And meaning doesn't require permanence. It requires only being present, being conscious, being alive to experience and understand and appreciate. The universe is mortal. So are we. That's the truth dark energy teaches. But here's another truth. Mortality doesn't equal meaninglessness. Temporary doesn't mean trivial. Brief doesn't mean unimportant. We exist now. The universe exists now. That's enough. Make the most of it. Create, explore, learn, love, wonder. Push back against entropy as far as physics allows. Leave the universe a bit more interesting than you found it. Dark energy will win eventually. But for now, for this moment, existence continues. The stars still shine, and we're here to see them. That's the real final word. Not that everything ends, but that before it does, we're alive, we're thinking, we're understanding. We're part of the universe awakening to its own nature, contemplating its own mortality, finding beauty in truth, however stark that truth might be. And that improbable, temporary, doomed but precious consciousness is worth everything. The universe is dying. Long live the universe, and long live us, who understand both the dying and the beauty, who face cosmic mortality with clear eyes and full hearts, who make meaning despite meaninglessness, who shine brief lights against the gathering dark. Dark energy will extinguish those lights eventually, but not yet, not today. Today, we exist, and existence, however temporary, is enough.